When working with continuous variables, we can use the probability density function or the cumulative distribution function to compute probabilities. Let's look at a few examples to see how that works. This is the first example. We have a continuous variable with probability density function f of x. For all x's less than 2, this function is equal to 0, and for all x's greater than 2, this function is equal to 2 over x squared. And here you can see what this graph looks like. Well, let's take a look at the first probability to compute. And let's say that we want to compute the probability that x is between 3 and 5. Now, with such a probability density function, this probability is actually equal to the area under the graph between the values 3 and 5. And so let's say that 3 is over here and 5 over here. Then this probability is given by this area over here. And that's actually the meaning of the probability density function. Well, and you all know how to compute such an area, the area under a graph. You do that with an integral. So in this case, we get the integral from 3 to 5 of the function 2 over x squared. Now, this is not a very difficult function to integrate. I think you can all compute that the antiderivative of 2 over x squared is actually minus 2 over x. Okay, if you plug in the boundary values 5 and 3, then we get that this probability that we're looking for is actually minus 2 over 5 minus 2 over 3. So that means minus 2 over 5 plus 2 over 3. And if we put this on a common denominator of 15, then we get minus 6 over 15 plus 10 over 15, which is 4 over 15. Let's look at one more example. In this case, we'll look at the probability that x is at least 4. You can say here too, this is actually the area under a graph, under the probability density function. Let's say that this is 4. And we're looking for this area over here. So in this case, it's a little bit different because, well, in this case, the area is unbounded. So that means that we will have an improper integral. So in this case, we once again integrate the probability density function, but here the boundaries will be 4 and plus infinity. Because if x is at least 4, that means that x lies between 4 and plus infinity. We already computed the antiderivative. That was minus 2 over x. And if we now plug in the boundary values, 4 and plus infinity, if you plug in infinity, we get minus 2 over plus infinity, which is actually 0, and then minus 2 over 4. So we get 0 plus 1 over 2, so a half. Here we use the probability density function to compute probabilities, but how can we use the cumulative distribution function? Let's take a look at an example. Once again, we have a continuous variable, but in this case, we use the distribution function that we usually denote with a capital F. In this case, this function is defined as 0 for all x's less than 0, x to the power 3 for all x's between 0 and 1, and it's equal to 1 for all x's larger than 1. As you can interpret this as a continuous variable that only takes on values between 0 and 1. What does this function look like? Well, something like this. So if we draw the graph, we have 0 for all x's below 0, then x to the power 3, looks something like that, and then it's equal to 1 for all x's larger than 1. Now in this case, the graph isn't that important, as the probability density function and the area under the graph represented certain probabilities. But in this case, what is the meaning of the distribution function? Well, by definition, f of x of some number a is equal to the probability that x is less than or equal to a. And so that's how the distribution function is actually defined. Well, let's take a look at how we can compute some probabilities with this distribution function. For example, let's start with the probability that x is at least 1 over 3. Well, the distribution function gives us the probabilities that x is less than a certain value. And here we need to compute the probability that x is more than a certain value, in this case 1 over 3. Well, luckily we can use the complement rule to compute this probability. So we can rewrite this probability as 1 minus the probability that x is less than 1 over 3. Now you see here that the distribution function is the probability that x is less than or equal to a, and here we have a strict inequality. And for continuous variables, this doesn't really make a difference. So we can change this to x is less than or equal to 1 over 3. Now keep in mind that for discrete variables, this distinction is important, but here we can ignore it. Well, now we just plug in the values that we have. So we have 1 minus our distribution function f in 1 over 3. Here you see that for all x's between 0 and 1, and the distribution function is defined as x over 3. So this means that in this case, we get 1 minus 1 over 3 to the power 3. So that's 1 minus 1 over 27. Or 26 over 27. Let's compute one more probability, and in this case, we'll look at the probability that x lies between 1 over 3 and 1 over 2. We want to use the distribution function, so we want to rewrite this probability in terms of probabilities that x is less than a certain value. Well, if x lies between 1 over 3 and 1 over 2, then we can rewrite that as the probability that x is less than 1 over 2 minus the probability that x is less than 1 over 3. And here too, we can change this strict inequality to equal or less than. Well, and now we can use the distribution function to compute this probability. We plug in all the necessary values, so the probability that x is less than 1 over 2 is 1 over 2 to the power 3 in this particular example, and the probability that x is less than or equal to 1 over 3 is 1 over 3 to the power 3. So we get 1 over 8 minus 1 over 27, and that is equal to, if you compute it, to 19 over 260.